And last but not least, somebody who does not come from UPC, but you still have to be very nice to him because his advisor was Yale. So, and Yale is right here in front of you, so be nice to him. So Onur comes from Switzerland, from ETH. Got his PhD, as I just said, with Yale. Yeah, okay. I know that. Okay. All right, Onur, shoot.
Okay, thank you. Thank you, Lawrence. Oh, is this better? Okay, I'll try not to speak here. And thank you for inviting me, Mateo. Happy birthday. It's always great to be here in Barcelona. I think I'm standing between you and lunch, and I'm very hungry also. So let's get it over with, let's say. That means I can speak faster. Yale was suggesting you should just speak faster. But I think building on a friend's nice talk, this can be an unpredictable talk, but it will be fault tolerant. Meaning we can stop at any time and we'll be fail-safe. So I'm going to talk about memory-centric computing. And as several talks mentioned, computing today is bottlenecked by data. And data is really key for many applications. We're basically generating a lot of data. We want to do more stuff on the data that we generate. And we're basically overwhelmed in our systems. These are examples from neural networks. I find these very boring, frankly. Compute requirements are growing, memory requirements are growing. Interesting, fine. But there are other workloads where we're generating a lot of data also. These are more traditional. Graph analytics is increasing. And these systems are basically bottlenecked because of these. And on the mobile end, we have a lot of other workloads also generating data. And as a result, data is really causing performance energy bottlenecks. We do a lot of work in genomics, and genome analysis is, I believe, going to be very, very interesting into the future. And here, again, we're generating a lot more data than we can process, and this is going to be even bigger into the future because we have these data generators. So I think of the world as data generation capability has increased. So this is a data generator that's extremely powerful, that's everywhere. There are other data generators that look like this in genomics. In video, we discussed video yesterday. Video has a lot of data generators. Internet is a huge data generator. Basically, we have special purpose machines for data generation, and we're feeding general purpose machines for data analysis, and as a result, we're very bottlenecked. An accelerator is one way of handling it, but there's a bigger problem, which is this movement of data from the data generator to the data analysis machine, as well as within the data analysis machine. So we're moving data all around in the entire world at the macro scale, as well as the micro scale in our machines. So we have a big problem basically going into the future. And this picture is similar for many other data generators and analyzers today. So I can talk about genome analysis, but I'm not going to do that. I think this is fascinating. I'll talk about a more fundamental thing. Basically, data is overwhelming our machines, storage capability, communication capability, and the computation capability in the end. It's also affecting robustness, energy, performance, and cost greatly. And if we go back to the fundamentals, we need all of these components in a machine. But we focused maybe a whole lot on the computing units and ignored the rest of it in the grand scheme of things. And this is my cartoonish picture, a bit old. Basically, this shows that the computation units are a very small part of what we design today. Those are the cores over there. Everything else is dedicated to moving and storing data. And if you do the calculations, more than 90% of a single node's real estate is dedicated to data storage and movement pieces, not computation. Yet, the system is still bottlenecked by memory and storage. So maybe we're doing something wrong. And if you don't like my picture, these are real pictures from real systems. This is AMD. And they keep adding more data storage units. This is a beautiful chip, IBM Power 10. Again, most of it is data storage and movement. This is Apple. I like this picture because I think this is a lot of SRAM, this is a lot of DRAM, and this is a lot of storage in the rest, which is not shown. And everything other than this part is darkness, meaning it's not intelligent, it cannot operate on data, right? It's just sitting there. Okay, so basically, we've done a lot of analysis on data movement in systems. This is one example paper we wrote with Google, and we show that more than 60% of the total system energy is spent on data movement, on these workloads that I showed you earlier. So what should we do going forward? I think we need to handle data well, and we need to do something different to not get overwhelmed by this data, not spend most of our energy resources, etc., on data storage and movement. So how to do better? Very quickly, I think we need to design better algorithms, better architectures, better whole system designs for applications, clearly. We need to take advantage of vast amounts of data and metadata flowing through the system to make our systems better over time also, because today there's a lot of data that's going through the system, but we're not learning from the data to make better decisions in our controllers. For example, when you design a memory controller, that's designed by a human. Human dictates what the memory controller does, but the memory controller doesn't learn anything over time. I have this a computer that's 6 years old. The memory controller is doing exactly what the human dictated to do, even though this memory controller could have learned from experience over the course of milliseconds, not even 6 years. Right? So as humans, we're learning from experience, but our designs are not learning from experience. I'm not going to talk about this, but I think this is very synergistic with what I will talk about. And I think we also need to better understand, exploit properties of different data and make decisions in our systems that are based on the properties of data. Again, I'll pick on the example of a memory controller. A memory controller makes a decision based on whether the DRAM bank is busy, whether the row buffer is open, whether there's a request that's, let's say, older. But it doesn't say, is this data more important for the application to process quickly, let's say. It doesn't say, is this data more security critical? So that sort of semantic information does not get communicated into our hardware. So in the end, I think we're very processor-centric versus data-centric. I'm going to talk about the first part a lot more. Today, we're designing systems that are making designer-dictated decisions versus data-driven, experience-driven decisions. And today, we're designing systems that are making component-based myopic decisions as opposed to data characteristic-aware decisions because they're not aware of the semantic importance of these characteristics. So I think the future, it needs to be a lot more data-centric, data-driven, and data-aware. I'm going to talk about especially the data-centric part. But I think to achieve all of this, we really need to rethink what we're doing across the transformation hierarchy. But I believe that we can get there step by step also. We're not going to overhaul this overnight, let's say. Okay, let me jump into the first part of it, which is the data-centric part. Even if you look at the data-centric part, I think there are many, many properties that we want. I'm going to focus on the first one and ignore the rest for now, but we can talk about it. So I'm going to talk about processing data where it resides, where it's generated, where it's stored. Or you can call it processing data where it makes sense. Clearly, this is an old idea. It's not a new idea. These are some old papers, the earliest papers that I could find on the topic on processing in memory. If you find any older one, please let me know. I'm always interested in knowing more. Another one that's concurrent is Harold Stone's paper. Basically, people have proposed the idea of processing in memory, and it has not panned out as much over the course of 50 years, as you can see. But it's happening now, in my opinion. And why is it happening now? Because we're having a lot of difficulty in the memory technology. Scaling is not going well. We're having a lot of reliability issues, vulnerabilities like RowHammer, and many scaling issues demand more intelligence, more intelligent controllers in memory. And at the same time, we're having a huge pull from applications and systems. Data access is a major bottleneck. Systems are energy and power limited, and data movement consumes a lot more energy than computation. This was mentioned yesterday also. Per mentioned it, for example. And at the same time, we need performance, energy, sustainability, all at the same time. We don't want to give up, basically. We don't want to go into a trade-off of performance and energy going into the future, in my opinion. We need to improve both of them at the same time. I think we can improve all metrics by minimizing data movement. So basically, today, we're squeezed in the middle. Technology is not going well. Applications and systems are bottlenecked. As a result, we're squeezed in the middle. And as a result, I think the landscape is changing. So people are building 3D stacked architectures, experimenting with chips, and more recently, general purpose processing in memory architectures have started appearing. More special purpose architectures have started appearing also. I'm going to mention these in a little bit. And I think we're going to see more of these into the future. Both manufacturers as well as big internet companies are looking into processing in memory. And there are many other experimental chips and startups that are not depicted over here. Okay, I'm going to skip some of these, but jump into basically what we want, let's say. So do we want a future that looks like this or that looks like this? I would argue that, again, we don't want a trade-off. We want high performance, energy efficiency, and sustainability at the same time. So the problem is the way we're looking at data, the way we are designing our computers, our design principles cause great energy waste today because we're moving data all around, as we discussed. But to tolerate that, we're making our computers more complex. So we put all these mechanisms, like heavy out-of-order execution, many levels of cache hierarchies, many levels of multi-threading, and prefetching. All of these things complicate the system. They try to alleviate some of the performance loss, but a lot of the times they don't work. If you have, for example, random access, none of those mechanisms work except heavy levels of multi-threading maybe. As a result, we're basically in a vicious cycle. Data access is hurting us in terms of energy and performance. To overcome the performance loss, we're complicating our machines, and that increases our energy waste also, because a lot of the times those parts of the machines that are dedicated for this purpose are not being used. And remember that the part of the machine that is dedicated for this purpose is huge. Okay, so I think we need to solve the problem at its root, meaning identify the problem, processing of data is performed far away from the data, and fix it. So I'm going to skip this also, I've already said some of this. And just to give you some numbers, I think we're designing better and better machines, no question about that, but our machines are still waiting for data. So this is a paper I like from Dick Seitz from 1996. It's a one-pager. After his team designed the flagship alpha processor, he wrote this paper saying that we designed this processor, it is capable of finishing four instructions per cycle. But on this important workload that we think we designed this processor for, it's finishing one instruction every 4.7 cycles. Why? Most of the time it's waiting for data to come back. And this story repeats itself. This is data from my, he finishes the article saying that I expect that over the coming decade, memory subsystem design will be the only important design issue for microprocessors. That's his quote. This is data from my own PhD thesis. With Intel, we analyzed their workloads at the time, and most of the time, again, the processor is waiting for data. And this is data from Google 10 years later, showing essentially the same thing. On the top of the line processor that they employ in their data centers, most of the time the processor is waiting for data to come back on all of their workloads, according to them. Again, all of their data center workloads. So energy perspective is even worse. This is a slide that I borrowed from Bill Daly that shows basically that a memory access consumes between 2 to 3 orders of magnitude the energy of a complex addition. And that's a complex addition. If you look at a simple addition, the number is actually much worse. Basically, a memory access is 6,400x more costly in terms of energy than a simple integer addition. And as a result, applications are suffering, and the systems are suffering. Most of the system energy is spent on data movement. The 62% is actually, let's say, optimistic. In some workloads, 99% of the energy is spent on data movement across the hierarchy. So I would argue that we do not want to move data. We need a paradigm shift to enable computation with minimal data movement, compute where it makes sense, and make computing architectures more data-centric. Of course, this is easier said than done. We want, at least to start with, memory as an accelerator. We already have a lot of, I think we need to look at the entire memory hierarchy, but main memory is interesting because we already have applications that are designed to fit in memory databases, in memory graph processing, in memory machine learning, in memory media processing. So people are fitting these applications inside the memory already as much as possible. So we would like to query the memory so that we can actually do operations, and the memory returns the results. So there are clearly many questions over here, which I'm not going to answer here, but there's a lot of research that can be done over here also. This is again across the stack. I will mention that we definitely need to design algorithms to fit the hardware, and hardware to fit the algorithms as well. But we also need to think about the theoretical foundations of computing, because theoretical foundations of computing have been very processor-centric. We're really counting operations to quantify our algorithmic complexity. Okay, there's a lot of work that goes on. I'm not going to talk about that in detail, but I will mention two different approaches to processing in memory. One is processing near memory, and the other is processing using memory. And I think there, if you find another one, please let me know. Processing near memory basically is very similar to what we do today. You have memory designed as memory. You have processor designed as processor. You keep putting the processor closer and closer and closer and closer. So the programming model doesn't change significantly. That processor can be whatever you want. It could be a CPU, GPU, FPGA. But processing using memory is fundamentally different, and it may require different programming models. The idea over here is what Ronnie talked about yesterday, for example, in terms of memristors. But memory, we think of memory as memory. It stores data, right? Why don't we think of memory also as a computation device? Because any memory has the capability not only to store data, but also do some computation. For example, the memristor has the capability of not storing data, but also it can do bitwise NOR operations. DRAM not only stores data, but it can also do bitwise majority operations. So the idea is to use the analog operational properties of the memory device so that you can do computation in the device as well without adding any logic to it. So I think this is really longer term. This is shorter term. As a result, we're seeing a lot of shorter term efforts for processing near memory. And this is easier to program to begin with, and this is harder to program to begin with. But in the end, if you really want to take advantage of processing in memory, I believe you really need to combine both of these approaches because they're really orthogonal and complementary. So let me quickly go over some works and then we'll conclude. So in both approaches, we're thinking memory as an accelerator still. Maybe that needs to change going into the future as well. Let me give you some examples of processing in memory that's happening in the real world, very quickly, an overview. So there are certainly real chips that are being designed. We've been working a lot with the UpMem company, which is a startup based in Grenoble in France. And they've been quite aggressive, actually, in terms of how they modified the DRAM chips. They have these modules, DRAM modules, and these are real. We've been experimenting with them, writing papers. And this is one example of this is essentially inside the DRAM chip, a single DRAM chip. You can see the single DRAM bank over here. Next to each bank, you have a processor. Essentially, it's a general purpose processor. It's a multi-threaded processor. It comes at an area overhead. It runs at 400 megahertz right now. So it's 10x lower than an existing CPU. But basically, you can program this using a version of C, and you can basically run workloads on it. And that's what we've been doing. We've been looking at different workloads. I'm not going to bore you with the workloads. You can actually find, Juan has been working on this quite heavily. He's giving a lecture later today in Pump School, actually. He's been doing that for years. But the issue here, you can minimize data moment if you program it well, but you're very compute bound. So this architecture is running at very low frequency because of the limitations of the DRAM technology. It doesn't even have a proper multiply instruction. It doesn't have floating point. It has an 8-bit multiply. As a result, the suitable workloads are memory bound. You need to be very careful. You need to use simple operations. And you need to minimize communication because the communication substrate across the DRAM banks is not very sophisticated, let's say. Even then, we developed a benchmark suite for this. People can contribute to it. It's all open source. Even then, you get significant performance benefits compared to existing CPUs and GPUs. I don't have the results over here, but there are some workloads where you can actually get significant performance benefits, even though there's a lot of downsides to the architecture. More recently, we've been looking at machine learning training on the same system, and we actually see you again need to fit your workloads to make sure they work well on the system. You need to optimize the data representation, use lookup tables as much as possible so that you avoid arithmetic, optimize data placement and layout, and you still get large speedups if you optimize the system, even with its downsides, let's say. So if you're interested, there's more on this, and we've been writing papers. We've been also looking at sparse matrix vector multiplication. As you can imagine, it's a tough workload for this system. So you really need to figure out what works and what doesn't work. And we release all of these workloads, libraries. If people are interested in working with them on a real processing in memory system, it'd be great if you contribute. Okay, so that's not just UpMem, Samsung. These are not openly available. UpMem is openly available. So if you want to work on the UpMem system, I think UpMem would be very happy to provide you access. Samsung also has its more specialized machine learning accelerator in processing in memory. They call it FIMDRAM. There's also information on it if you can. They have a very simple, let's say, instruction set architecture. This is very different design point. It can do multiply and accumulates, for example. Very different from a floating point multiply and accumulates compared to UpMem, which is not able to do any floating point. So the design points are very different in these real architectures. Samsung also worked with Facebook to have these DRAM modules that can do recommendation system acceleration. And SK Hynix also introduced their own processing in memory machine. And more recently, Alibaba also introduced their own processing in memory. These are all DRAM-based systems. They basically change the DRAM chip so that they can do acceleration for various reasons. There are also many, many experimental chips that are RRAM memristor-based. Okay. So if we have some time, I'll mention processing using memory. Otherwise, we can conclude. How much time do we have?
We are late.
Okay, we started late. Okay, maybe I'll.
Sorry.
Say it again.
Because we have only 1 hour for lunch.
Okay.
1 sentence.
Oh, one sentence is hard. Okay, so let me actually get the gist of it over here. So basically, you can exploit the analog operational properties of memory to do data copy internally inside the memory. That's the idea over here. So how do you do it? Let me get to the gist of it. So we're wasting a lot of time on data copy going through the memory controller today, right? Why not do it inside memory? If the source row is in the same subarray as the destination row, bring the source row to the row buffer by doing an activate, and then do another activate, which brings the data that was copied into the row buffer from the source row into the destination row. By doing 2 consecutive activates, you can basically, at negligible hardware cost, you can basically reduce the copy latency by an order of magnitude and copy energy by almost 2 orders of magnitude. So this is very interesting, I think. Now, the more interesting part is, after we proposed it, people actually showed that you can do it in real DRAM chips without changing the DRAM chip by reducing the timing parameters, violating the timing parameters. And we built on that work to show that you can actually do end-to-end evaluations of row clone, true random number generators, and also bitwise majority functions using a substrate that's FPGA based. We actually released the substrate. You can play with it. It's a real system, and you can do end-to-end evaluations of these. And you see significant speed-ups. These are micro benchmarks, but we have real benchmarks in the paper as well. You can basically improve the initialization and copy throughput in this real system significantly. Okay. Maybe I'll mention this also, and then we'll be done. So you can say that that's data copy initialization, but you can also do computation. And this requires a little bit more change to the DRAM, but you have analog computation capability in DRAM. And other technologies are quite interesting. As Rouhani talked yesterday, memristors are quite interesting, for example, but all of the technologies are capable of some analog computation, even though they're designed as memory. So with DRAM, the primitive is triple row activation. So basically, if you have 3 rows in DRAM, if you concurrently activate those 3 at the same time, because of charge sharing principles of the circuit, you get a majority function. So it's bitwise majority, essentially. And bitwise majority is good because you can express your algorithms in terms of bitwise majority, except they won't be complete because you're missing a NOT, right? Majority and NOT are functionally complete together. And majority can be expressed as AND or. If you set C to 1, you get the OR of A and B. If you set C to 0, you get the AND of A and B. So you can also implement the NOT function because NOT is already complement of the data, already exists here actually. You can feed it to some other subarray, or you can feed it back to the subarray with some modification. As a result, you can have a functionally complete engine in DRAM. And again, you can get this majority function, or AND and OR more specifically, by violating the timing parameters in the memory controller. If you carefully violate the timing parameters in the memory controller, it turns out in some chips, real chips that are not designed for this purpose, in some real chips, 3 rows get activated, and you get a bitwise majority across those 3 rows. This is a small fraction of chips, but remember, the DRAM was not designed for this purpose. We're violating the timing parameters. So if it's designed for this purpose, imagine what you can do. So this is good for especially applications that use bulk bitwise operations, so you get significant performance improvements. I'll mention one thing about programming. So this is interesting, but the difficulty here is programming. So how do you actually enable a programming framework that can take advantage of this? Recently we worked on it, and we can actually generalize it to any operation, because any operation can be expressed as AND or NOT logic. So you can express convolution, for example, and the convolution gets expressed with this logic, and we have an optimizer. We use actually optimizers that were developed at EPFL based on the majority inverter graph. It optimizes the majority NOT functions and minimizes the DRAM commands that you need to actually execute a particular function. This could be multiplication, this could be convolution, it could be division, it could be anything as long as you can express it this way. And then we generate a microprogram that's stored in the memory controller that can be executed when that function is called by an instruction in the program. So basically, you can integrate it into the sequential execution model by having an instruction, and that instruction gets shipped to the memory controller, and the memory controller invokes the microprogram that you have optimized so that it basically executes the DRAM commands that are needed to achieve the function. And I think this eases programmability significantly. It also generalizes the mechanism. Now you can implement any function. Some of them may not be very efficient though. Division, for example, is not very efficient because it's bit serial. But we still see a lot of performance and energy improvements compared to a high-end GPU as well. Okay, so I can talk more, but I'm going to stop here. I will just mention that adoption issues are very important in both of them, and there are lots of adoption issues. And the goal is to solve these adoption issues. There was a talk by on GPUs from Dave Cayley. I think of processing in memory as what GPUs looked like 20 years ago. So we're at the baby steps. Right now, 20 years ago, very specialized people were trying to make use of GPUs and make them general purpose, right? I think we're at that point right now in processing in memory. Hopefully it will not take 20 years, but we'll see. Okay, the goal is to get there step by step. Okay, I think I'll stop here because we're out of time. I'll just mention this last one over here.
So, Onur, that was quite one sentence, huh?
Yeah.
So, Onur, you started off by saying you have lots of data. Clearly, it's not going to be in DRAM. So why don't we just compute on disk?
Yeah, absolutely. So, okay, I just gave you examples from DRAM. I think that's one place we should be looking at, but storage also, absolutely. We've been looking at storage, for example. I didn't get a chance to talk about that. There are some cases where your data movement between the storage and memory and the CPUs is a huge limiter, and computing in storage buys you a lot of performance in that case. I think we should be computing everywhere.
Yeah, this was kind of my question. Thanks, by the way. Why don't you compute in the devices itself, right? I mean,
yeah.
The data arrive, I don't know, through Ethernet or PCI. I mean, could some computation be done there?
Yeah, absolutely. I gave you a lot of examples from memory because I think memory is a tough part, but we should really be computing at the sensors when we're sensing the data. All of those data generators. For example, I showed you the sequencing device earlier, right? That has no computation capability. But if it actually does some computation to do some base calling, for example, it eases the work for the other devices that come down. Of course, the capabilities of the devices may be limited in terms of the type of data analysis that you need to do. So you need to figure out what kind of computation that you do in this device. Same with cameras, right? There are a lot of cameras that can filter out what may be going on, especially if you know what kind of application that you're going to use on top of the video. Sure. Sure. Sorry, I couldn't hear. Trevor.
How do you see near-memory computing? Do you see the near-memory computing? How are you going to handle virtual memory? Are they working on bit? Are they aware of virtual memory? Or?
That's part of the adoption issues. I think actually virtual memory is the toughest one, Trevor. I think we really need to rethink virtual memory in general, independently of processing in memory or near memory, because we're having a lot of scaling issues with virtual memory in our systems. There's a lot of overhead. But yeah, once you start offloading stuff.
Virtual memory is also CPU specific.
That's exactly. It's a very compute-centric paradigm today, right? We need to make it more distributed. So I think there's a lot of research that can be done on the virtual memory area. I don't have a good answer to you. Like in the UpMem system, it's physical. There's no, yeah.
Yeah, a very basic level question. Since you are doing computation in analog field, you're gonna do that. So a very basic level question: is it difficult to deal noise in analog domain rather than digital?
Yeah, absolutely. It's harder. And that's part of the challenge that needs to be solved for these analog computation devices. That's one of the reasons it's difficult to get. So, for example, the row copy that we discussed. In the chips that it works reliably. But once you go to the majority function, in the chips that it doesn't work as reliably. I think part of the reason is the analog noise that you have. So these chips need to be designed so that they're more tolerant of noise, and error correction capability needs to be added also on top of that.
Okay, I think that we should thank Onur.
Thank you. Thank you, Matteo.